Wrong. Yeah, we buy them in bulk. I got 4 or 5 of these.
It's like a puzzle. Kind of neat. I give you lots of things. Get to even little things in like work with a big puzzle.
Okay, let's begin. Let me have your attention. Let's begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Colloquium Program. Today's speaker is Dr. Tom Mason, who's the Associate Laboratory Director at the Oak Ridge National Laboratory with responsibility for the Spallation Neutron source. Tom received his PhD in physics from McMaster University in Hamilton, Ontario, and a BS in physics from Dalhousie University in Halifax, Nova Scotia. He has worked for AT&T Bell Labs and also at the RISO Laboratory in Denmark. Before joining the SNS project in May of 1998, he was a faculty member in the Department of Physics at the University of Toronto. And for most of you who don't know, the Spallation Neutron source is the largest scientific related construction project in the United States. And that is the subject of his presentation today, the Spallation Neutron source, a powerful tool for materials research. Tom, welcome.
Thank you. I guess there's 3 parts to what I'm going to talk about. I'm going to start off with a bit of a background about spallation sources and some of the history and the development of, first off, with some ideas that never quite got off the ground, and then more recently with some that did. I'll say then a little bit about SNS and what it is, what it will be, and how things are going, and then I'll conclude a little bit talking about some of the science we hope to use the facility for once it's up and running in about 4 years' time. SNS is a tool that is being built by the Department of Energy's Office of Basic Energy Sciences to study the structure and dynamics of materials using the scattering of thermal neutrons, thermal or cold neutrons. And the reason that we do that, whether I'm a condensed matter physicist, chemists, biologists, material scientists, and engineers, all have interests in problems that really at their base depend on understanding the structure of materials in terms of the crystallography at an atom-by-atom level. So the simple illustration of that is to consider the case of carbon, which, as you all know, comes in 3 different forms. Of course, graphite is a layered structure, so there's hexagonal sheets that are stacked one on top of the other. And graphite is black, it's opaque, it's soft, it's used as an industrial lubricant, and it's very different from diamond, which is exactly the same stuff but arranged in a 3-dimensionally linked cubic structure. And of course, more recently, you have buckyballs, which are another form of carbon, a little bit like a graphite sheet rolled up into a ball, but its properties are as different from graphite or diamond as graphite and diamond are from each other. So over the years, a number of techniques have been developed and are used for understanding structure. X-ray diffraction is probably the most widely known. You can use nuclear magnetic resonance, electron diffraction, scanning probe microscopies to image at least surfaces in real space. But neutrons are one of the probes that we use. The neutron was discovered in 1932 by Chadwick, who was working in Rutherford's laboratory studying radioactive decay. And actually, it was very soon after that, in 1936, that 2 groups working independently demonstrated the coherent diffraction of neutrons from crystal lattice planes. And that was done as an exercise in wave mechanics, understanding and demonstrating the fact that the neutron had a de Broglie wavelength and therefore it could do a wave-like thing, i.e. diffract. It wasn't done to understand the crystal lattice from which they were diffracting. The possibility of using the scattering of neutrons to probe the structure of materials really only became viable with much higher intensity sources. And that was sort of a spin-off from the Manhattan Project and the fact that you had in in a reactor a moderated source of neutrons that was quite a bit more intense than one could access with a radioactive source. So after 1945, Fermi's group began to use Bragg scattering to measure nuclear cross sections, and so we have the Barn book, for example, and a lot of those measurements were done as an effort of cataloging neutron cross section for the purposes of making reactors and bombs. But you were using, in those cases, powder diffraction actually as one of the methods of doing that. Of course, the key is that the reactor moderates the neutrons produced in the fission chain reaction, and you come into thermal equilibrium with a Maxwellian energy distribution that's centered on the temperature of the moderator. So if you're at room temperature, 300 K, that turns out to correspond to a neutron with a wave number of 10 to the minus 10 meters. So if you plug in some numbers, you find that neutron that's the most populated, if you will, has an energy of about 25 millielectron volts, corresponding to a wavelength of 1.8 angstroms. And of course, 1.8 angstroms means the wavelength of the neutron is comparable to the interatomic spacing in materials, and that's why you can diffract. Of course, you can play games and, for example, introduce a cold source into your reactor, which would be an aluminum can filled with supercritical hydrogen or deuterium. And that has the effect of shifting the Maxwellian down to lower temperatures or energies and longer wavelengths. And in fact, that's quite productively employed in cases where people want to study materials that have structural features on longer length scales and therefore longer wavelength neutrons. Using neutrons to study condensed matter in the sense that we now do it really had its birth in the work of Woolen and Shull and on neutron powder diffraction. This was carried out in Oak Ridge using the graphite reactor, or the Clinton pile as it was called. And this figure shows some data taken from their 1948 paper in Physical Review on neutron powder diffraction, where they've plotted the intensity in counts per minute of a monochromatic beam of neutrons scattered off a sample of polycrystalline aluminum, plotted as a function of scattering angle. And what you see are these sharp diffraction peaks, each one corresponding to a particular lattice plane in the aluminum. And that's the sort of thing you can use to deduce the crystal structure of aluminum. Now, in 1948, the crystal structure of aluminum was well known. It had been studied by X-ray diffraction, and in fact, a lot of that work had been carried out many decades before. The point was, and this is what Woolen and Shull highlight in the paper, because the coupling of neutrons to matter is quite different from photons, i.e. X-rays, the things that you are sensitive to are quite different from what you're sensitive to with X-rays. So although aluminum wasn't necessarily particularly interesting in 1948, they did realize that there were things that you could do better with neutrons than you could address with other techniques. And so I'm going to run through what some of the issues that impact that are. The first thing is that the neutron is weakly interacting because it's not a charged particle. And because it's weakly interacting, it's non-perturbing. Therefore, you don't damage the sample. We're talking about thermal neutrons here. And the coupling to atoms is really a coupling to the nucleus. And you can also, because the neutron has a magnetic moment coupled to spins in solids, it's very simple and well understood. From the point of view of a biologist or a condensed matter physicist, a nucleus is a point object, and so the scattering potential that you scatter function from is a delta function. So it's the simplest possible thing to analyze mathematically. Similarly with the spins, it's just dipole-dipole interaction. You can write down exactly what the interaction is, and that means that the scattering experiment tells you about the sample and not the probe, or not the probe plus the sample. It's a very clean and interpretable sort of thing. Because the neutron is neutral and it penetrates, you can easily work in extreme sample environments. So there are experiments done at high magnetic fields, very low or very high temperature, very high pressures. An early example is the first low temperature neutron experiments done by the same two scientists, Cliff Shull and Ernie Woolen. And Cliff Shull shared the 1994 Nobel Prize in Physics for the work that he did at Oak Ridge in developing the technique. And also you can penetrate into dense samples, so it's possible to do measurements deep inside intact engineering components. And neutrons will go through inches of steel and feet of aluminum and still be able to get out again with appreciable intensity. So if you're interested in measuring, for example, residual strains in intact engineering components, you can do that and do it in large real things as a function of position. The cross sections, which determine the scattering, how the scattering intensity relates to things like atomic positions, are first off, magnetic and nuclear cross sections are essentially the same size, which is not the case with X-rays. And also, the nuclear cross sections are very similar across the periodic table. If you think of the case of X-ray scattering, what's shown here, starting with hydrogen, carbon, oxygen, so on down the periodic table. With X-rays, what you're sensitive to is the number of electrons. So as you go down the periodic table, the elements get more and more visible. So that means if you're trying to locate a hydrogen in the presence of, say, an iron, it's extremely difficult. No matter how intense your X-ray source is, there's a sort of fundamental signal-to-noise issue that you have to grapple with, just because iron, or even worse, uranium, has a lot more electrons than the hydrogen, which is just sitting there with one. In the case of neutrons, this shows the neutron cross-sections for the same elements, except now we need another axis because you have more than one isotope and you're scattering from the nucleus. So, for example, for hydrogen, you've got hydrogen and deuterium. Tritium isn't shown, but in any case, they're different. And similarly, you have different isotopes of the other elements as well. But by and large, as you move down the periodic table, they're all roughly the same size. And also, the cross-section is not correlated with where you are in the periodic table. So you don't have this systematic variation that correlates with chemical properties and so forth. So from the point of view of a chemist, this is random, actually. It's not random. It has to do with the constituents of the nucleus and how many protons and neutrons you have, but that has no impact on the structure of a protein. The fact that you have this isotopic variation, and it's larger than it looks because it's a little hard to see, but actually this one is shaded. That's because hydrogen has a negative scattering length. So not only is hydrogen and deuterium different in magnitude in terms of the scattering cross-section, but there's a phase shift that takes place in the scattering that basically means you could not have two more different things from the point of view of a neutron than hydrogen and deuterium. Now, we know that well from heavy water versus light water reactors. But the other thing we know is that, again, from the point of view of the behavior in a polymer or in a protein, it doesn't make a whole heck of a lot of difference whether it's H or D. So you can selectively deuterate and really enhance the sort of signals that you get to give you very specific, site-specific information about the structure. So overall, you have sensitivity to a wide range of properties, both magnetic and structural. I already mentioned that the energy of a thermal neutron is typically around 20 or 30 millivolts. If you take a cold neutron, then you're more like maybe 5 millivolts. Those energies, just like the length scale maps onto the interatomic spacing, the energy scale of neutrons map onto the low-lying vibrational modes in materials that are responsible for things like sound velocity, what we call the phonons and so forth. So it means you can simultaneously resolve in energy and momentum. So you have access to the whole sort of four-dimensional space-time world that we live in. And certainly if you're interested in things like phase transitions, then excitations who have energies of order kT are important for driving phase transitions. So in addition to the structural utility of scattering neutrons, you also have this ability to do dynamics and look at the thermodynamically relevant excitations. The inelastic scattering part took a little longer. The stuff I showed you on diffraction was begun in the 40s with the first generation of research reactors. Inelastic scattering is about 3 orders of magnitude weaker than elastic scattering, so you need to move on to the next generation of research reactors before that's really viable. So that happened throughout the 50s. And a lot of that pioneering work was done at Chalk River by Brockhaus, who shared with Schull the '94 Nobel Prize in Physics. And that really permitted the systematic investigation of dynamic response as well as the statics, i.e. the structure. There are 2 methods by which neutrons are produced for doing this sort of scattering research. Of course, you can get neutrons other ways as well. But the 2 that are primarily used are, of course, fission where you have a thermal neutron that interacts with a fissile nucleus like U-235. That breaks apart. You have liberated a larger number of neutrons than you started with, so you can sustain a chain reaction. And in fact, you can cut a hole in the side of your reactor and steal some of them and still sustain the chain reaction. And so that's the traditional route, if you will. Basically, you have available to you in your beam port of order 1 neutron per fission. If you let too many leak out, then you don't have a critical reactor anymore. And with very few exceptions, and there are some, reactors tend to be CW, continuous source of neutrons. They're basically on all the time. There are a few exceptions to that with pulse reactors, but generally that's the case. In the case of spallation, there's no chain reaction. You're driving a reaction with a high-energy proton beam, typically. So you have protons that are accelerated up to of order 1 billion volts, and then you have that interacting with some heavy nucleus, and it doesn't particularly matter which one. That's basically an engineering decision. And what happens is when that proton comes in, it can just knock neutrons out. It also heats up, if you will, the nucleus into a fairly highly excited state. And the way that that de-excites is by evaporation thermodynamically. And so it evaporates neutrons. The resultant nucleus is then unstable, so it goes on to decay. But you get 20 to 30 neutrons out for every proton that you send in. And of course, it's not a chain reaction because as soon as you turn off the protons, the whole thing stops. There's no ability to sustain the operation, so you've got to have an accelerator as a driver to produce these spallation neutrons. And typically, although not in all cases, that accelerator will operate in a pulse mode as opposed to the sort of continuous source that you would have with a reactor. This shows the development of the facilities over time, starting in 1932 with Chadwick and his radioactive sources. And what's plotted here is the thermal neutron flux in neutrons per square centimeter per second, and this would be sort of the peak thermal neutron flux right in the neutron-producing volume as a function of year. And what you see is that with the development of research reactors, you had this huge jump in neutron flux, and X10 is the graphite reactor. So that really enabled neutron diffraction, and it was the succeeding generation of research reactors that got you into the dynamics business. But then after that, things pretty much capped out, so that Pfeiffer, HFBR, and the Institut Laue-Langevin, which were built in the 60s and 70s, didn't represent actually a huge increase over some of their predecessors, and also since then we haven't seen any big increases in thermal neutron flux. And what's happening here is you're running into essentially an engineering brick wall associated with cooling the core. So you make the power density as high as you can, you run the cooling water through as fast as you can, and eventually you reach a point where you just can't have any higher power density, and that's really what limits the thermal neutron flux. Research reactors tend to be designed for really high peak fluxes and power density rather than overall average power, for example. The scientific performance continued to improve because a lot of the instrumentation was continuing to advance, but in terms of raw source performance, there was not much to be gained. However, in the meantime, this other route, spallation, began to get closer and closer to being viable. The difficulty historically was that you didn't have the accelerator driver. And accelerator technology has been advancing very rapidly. And so we're now in a situation where the world's best spallation source, ISIS, is very comparable and competitive to the world's best research reactor for neutron scattering, the Institut Laue-Langevin reactor in Grenoble. Whoops, I need to do that. And of course, we're not done yet. SNS is going to be a big jump forward over ISIS. It's probably not at any ultimate theoretical limit yet in terms of power density, certainly. And so we've kind of moved on to a new technology growth curve in terms of the source performance, and there's still headroom there for the future. So this is just recapping. So we've got our fission case, and this is kind of highlighting what I was talking about. When you're when you're doing fission of this type and you've got some of your neutrons available, roughly speaking, the amount of energy that you have to deal with on a per neutron basis, which you ultimately have to remove in the form of heat, is 200 million electron volts per neutron. So just keep that in mind, and I'll get back to it in a second. So the benchmark for a research reactor is the high flux reactor in Grenoble. It's got a peak thermal neutron flux in the core of a little over 10 to the 15 neutrons per square centimeter per second. It was just recently refurbished. They replaced the vessel. It was finished in the early 70s, but it's still got quite a productive life ahead of it. The advantages of this type of source is you have lots of neutrons, high time average flux. The technology is very mature, both in terms of the source and the instruments. And there's a sort of conventional wisdom that says if you want cold neutrons with long wavelengths, reactors are very good. The drawbacks are that it's hard to build reactors, even now as people are talking about, Renaissance and all that sort of stuff. It hasn't, people are still talking about it. We haven't seen the construction starts yet. And also, there's no time structure in the source itself. So if you want to work with pulsed beams, you've got to chop the beam, and that means you throw away a lot of the neutrons. So this shows an overview of the ILL reactor in kind of cartoon view. So it's a heavy water reactor. So this is the D2O tank. The core is right here. And the take-home message from this is that there are a lot of instruments. Each one of these lines is a neutron guide with, in some cases, 3 or 4 instruments on it. And so there's a very robust instrument suite. Each one of them is optimized for a different type of science, and it operates as a user facility that serves a very large and diverse research community in Europe. And it's got cold sources, 2 of them. This is the newest one, which is a great big liquid deuterium cold source. It's also got a hot source, which is just a lump of graphite that's placed adjacent to the reactor core, and it gets just heated up by the gammas to about 1500 degrees, and that shifts the Maxwellian spectrum the other way. So if you want short wavelength neutrons, then you sit on this hot source. If you want cold long wavelength neutrons, you sit on the cold source, and if you can't make up your mind, then there's thermal beams as well. There is a variant, which is a pulsed reactor. For neutron scattering, the only one I know of is in Russia, the IVR2 in Dubna. It ran initially at 2 hertz. They've upgraded it to run at 5 hertz. And when it's on, it's really on. It's a 1,500 megawatt reactor. For comparison, the ILL reactor is a 58 megawatt reactor. And so it has a very high peak flux. Turns out this time structure at 2 hertz or 5 hertz is not optimal. You could run at a higher frequency and get more neutrons that you could still use. So the average intensity is lower than it might be if you had the ability to choose the frequency, the repetition rate optimally. And it's hard to see how you could build this thing outside of Russia. This shows you the design. It's got plutonium oxide fuel in the fuel here. There's a reflector surrounding it. And then this is a reflector. These things that look like scissors are counter-rotating reflectors. And what happens is they spin around, and when they line up, then the reactor is critical. So that's the on position. And then when the reflectors rotate out, that's the off position. It's no longer critical. So the power cycles as these things spin around. And of course, then the question you have to answer is what happens if these things which are big, mechanical devices, get stuck in the on position, and you've got a 1,500 megawatt reactor with 2 megawatts of cooling capacity. But it does run, and within the constraints of difficult financial circumstances, they do a pretty good job of running a scientific program associated with it. So it's got an average power of 2 megawatts and a peak power in the pulse reflective of a 1,500 megawatt reactor. It never goes completely off, which is one of the issues. It sort of cycles, and it goes down to about 120 kilowatts in the off position. And it's got fairly broad pulses because it's just determined by this rather slow mechanical device of about 320 microseconds, which is in some cases okay. In other cases, it's a little longer than you would want for time resolving your neutron velocities. And this just shows the experimental suite. So it also has a range of instruments that view moderators in close to the core. Okay, so if we go to the spallation now, where you've got your 1 GeV proton and then your target material, existing sources use tungsten, IPNS uses uranium, depleted uranium. They've also run with enriched uranium, which sort of gives you a bit of a boost, but it's trickier. ISIS uses tantalum. They're all water-cooled solid targets. And you get of order 20 neutrons for every proton. And the energy associated with this on a per neutron basis is about 23 million volts. So if your limitation is your ability to cool the neutron-producing volume, then you're about an order of magnitude better off with spallation. It's sort of a thermally more efficient process in terms of getting neutrons out. And to compare the ISIS facility, it's tricky to compare it to a reactor because it's pulsed. So depending on whether you care about the total number of neutrons or the brightness when it's on, you get a different answer. If you look at ISIS, the average flux is down by nearly 2 orders of magnitude from the ILL reactor to ISIS. However, the peak flux is the other way around. ISIS is about 5 times more intense than the ILL reactor when it's on. It runs at 50 hertz, which is the line frequency in the UK. So it depends what your figure of merit is, and that depends how you design the instrument. In cases where you can make a good time-of-flight instrument, where you use the time structure to define the neutron velocities and hence their wavelength, you can actually make use of the peak flux with 100% effectiveness. And so in those experiments, ISIS is better than the ILL. There are some experiments where it doesn't work out that way, in which case you would have to look at the time average flux. And clearly for something like isotope production, where you don't care about the time structure at all, you're going to be better off with a high-intensity continuous reactor-type source than a pulse spallation source. So ISIS, and there's a facility at Los Alamos called Lance, which is very similar, runs with a proton accelerator with a current of 200 microamps, a little less than a GeV, and when you multiply these two numbers together, you get about 160 kilowatts. And then we have to remember that this is about an order of magnitude more thermally efficient in terms of neutrons than a reactor. So ISIS, in terms of its time average flux, is sort of like a 2 megawatt research reactor. Right? But when it's on, it's really on. So you have the advantages of a high peak flux. The time structure turns out to be advantageous for many applications, so that in many instances you can take credit for that peak flux. It's easier to build accelerators than reactors, depending on what country you're in. There are some places where you can still build research reactors. But generally people like this feature of non-chain reaction. The fact that there's an off switch, which is really an off switch, makes it easier to sell. The technology is rapidly evolving, and you sort of see that with the increased performance over time. So we've got improved performance, year to year. The disadvantages is that for the existing sources anyway, the time average flux is lower. Not all the applications can exploit the time structure, so sometimes this really does matter. And of course, if the technology is rapidly evolving, that can be a frustration as well as a benefit, depending on how things are going on any particular day. This shows an overview of the IPNS facility at Argonne, which has a LINAC injecting into a rapid cycling synchrotron that accelerates the proton beam up to 450 million volts, and then delivers it to a depleted uranium target. And then surrounding that is an instrument suite which is as diverse as the scientific community that the facility serves. And IPNS is, together with a comparable facility in Japan at KEK, those are the first 2 spallation sources that were reached a performance level where they could be broadly used for studying materials, as opposed to a kind of R&D demonstration type thing. And they both got started one was in 1980 in Japan, and then IPNS was right afterwards in 81. So they've been operating for a little over 20 years now. There is a variant which is a continuous spallation source. PSI in Switzerland has one of these. It's the only one in the world. It operates with a much higher current. In fact, they've increased even beyond this. They're up over a milliamp, I think, compared with 200 microamps for ISIS, for example. And so the power level, which is now up above a megawatt, so a higher power level. So this is more like a 10 megawatt research. It's actually like a 10 megawatt heavy water research reactor in terms of the neutron flux. So it's about 10 to the 14 neutrons per square centimeter per second. So with this continuous source, you have a higher time average flux than you do on the pulse source. The instrumentation looks exactly like what you build at a reactor. And in fact, they moved instruments from their research reactor, which was shutting down, the Sapphire reactor, to PSI. You don't have the time structure. There was a fear that you would have a high background because with a pulse source, the way it works is you make the neutrons with the proton beam, and then you wait for a bit and you begin counting them as they fly down your instrument. So you're doing all your counting when the beam is off, which is an advantage in terms of signal to noise. You can't do that with a continuous source. So there was a fear that, there's all kinds of crap produced in the spallation reaction, that the signal to noise would be a problem. They worked really hard on the shielding and got it right, so it hasn't been an issue in this case. And this shows a layout of the facility. It's based on a cyclotron that was originally built for doing sort of meson physics in the 70s, and feeds a whole bunch of things. There's a medical facility for doing experimental radiation therapy, and then down here at the end of some beam lines where they make muons and so forth, they have a neutron target, and the beam actually comes in vertically to a new water-cooled solid target at the moment. They're planning to switch to a liquid target soon, and then surrounding it is a big D2O tank, and there's also cold sources. This is shown here. The beam comes in from the bottom. They have this water-cooled, I think it's tantalum. They were running with zircaloy, but they've switched because zircaloy is not that great in terms of producing neutrons. Then you've got this big D2O tank, which looks an awful lot like the moderator vessel of a research reactor. And then they've got a cold source, and then there's some thermal beams as well. That's shown here in this top view looking down on the target. You've got the D2 cold source and the thermal beams that are just looking at water scatters embedded in this big tank. So aside from the fact that this is not a reactor core, it looks an awful lot like a research reactor. It's just driven by the accelerator. Okay, I'm now going to go back very quickly to go through some of the earlier history because it's kind of interesting. If you look back at the development of spallation sources, I think one of the earliest concepts was something called the Materials Testing Accelerator that was proposed by Lawrence in the late 1940s as a means of breeding plutonium-239 and tritium and U-233. Despite its name, it was never intended for materials research. I guess this was sort of a euphemism. The reason they wanted to breed these things is because at the time it was thought that there wasn't a lot of fissile material out there that you could go and mine. And so the development work was done at what's now called Livermore, where they did a lot of work that was important in developing high-power accelerators. And they continued to work on the concept until 1955, when uranium ore reserves were found in the U.S., and then the original driving need to have this breeder capability went away. And by that time, the pre-accelerator that they'd built had run proton currents up to 100 milliamps. They'd also run deuterons, which you can also do spallation with up to 30 milliamps. In 1957, it was declassified, and there's actually a Popular Science article that I'll show you a picture from that describes some of this. There was already, at that time, in the late 40s and early 50s, spallation was known. The fact that it's a very efficient way to produce neutrons was known. And it was also known that if you used deuterons instead of protons, you got an additional boost. So that was the choice that led them to this scheme where they were going to have a deuteron accelerator with a 500 MeV energy and very high current. I mean, this is extremely ambitious, 160 megawatts. That's well beyond anything that anyone's thinking about right now. Originally they started out thinking of a uranium target, and they've even looked at things like moderated subcritical lattices, which is an idea that's still around in varying forms today, particularly in Europe, but it's also being considered as a means of burning waste. And they eventually settled on, this is amazing, I mean, a sodium-potassium cooled beryllium primary target with a depleted uranium secondary target for neutron multiplication. So, these guys weren't afraid to mess around with nasty stuff. And the goal was to breed plutonium. This shows from this Popular Science article a cutaway view of their scheme. And the first thing you need to notice is that these are people. So this is really big. And the reason it's big is because the RF technology of the day was at much lower frequencies than we normally work with now. So SNS is working with 402.5 and 805 megahertz RF systems. So our resonance structures are about that big. Well, if you're working with lower frequency structures, then everything has to scale up, and so you wind up with resonant cavities that are several stories tall. There was another project that followed on at Chalk River called ING, the Intense Neutron Generator. That really got started in 1964. And Chalk River actually had the highest flux research reactor from about 1957 until sometime when I guess HIFER and HFBR came online. And their goal was they thought that neutrons were important for a number of reasons. They were developing reactors, and they just figured if you're going to have the highest flux neutron source, the next step is to go to spallation. So they had this ING concept that proceeded until about 68, when it just became clear that it was much too ambitious for the funding and political support that they were likely to get. But again, there were some important developments. This shows the concept. There's a 5,000-foot linear accelerator, a Maison experimental facility, and then the spallation target, which it turns out, anyone who's been to Chalk River, the research reactors there are all in buildings that look identical to this. So their concept was you just start with a reactor, except it's a bit like the PSI concept, actually. It looks just like a reactor, but it isn't. Their target was to be a liquid metal target, flowing lead bismuth eutectic. It's basically solder, with a vertical proton beam injection, a beryllium reflector, D2O moderator. And again, it was very ambitious. They were looking at a thermal neutron flux of 10 to the 16 neutrons per square centimeter per second, so more than an order of magnitude beyond the highest flux research reactor today. This shows the scheme with the protons coming in from the top, this reactor vessel-like thing, and then a few neutron beams that they didn't even bother to put instruments on in their conceptual drawings. And this shows the scheme for the lead bismuth flowing down, and then you set it up so there's a meniscus, and then you extract it out here to cool. And one of the things that they did as part of that was examine in measurements at the Cosmotron at Brookhaven, which is an accelerator, the spallation yield as a function of proton energy. And what you see for various target nuclei is generally heavier nucleus is better. There's more neutrons to knock out. And also, it more or less goes up linearly with energy. So you can kind of trade off energy and current. It's really power that matters. Now, turns out if you start going up to really high energies, up above 5 GeV or so, it begins to fall off. So somewhere between 1 and 3 GeV is about optimal in terms of neutron collection. Okay, so now we get to SNS. This shows an overview of the facility, and we're at the midpoint of construction. So an aerial photograph now would look a lot like this, except some of the buildings, there'd only be foundations, but in general, most of the shell is now there. It's based on a LINAC that does all of the acceleration up to 1 GeV, and there's sort of 3 different components to the LINAC. The front end is now in Oak Ridge. It was delivered from Berkeley, which was responsible for that part of the scope, and that produces the H- beam and accelerates it up to 2.5 MeV. And then delivers it to a LINAC, which has three different pieces. 2 of them are copper structures, a drift tube LINAC and a coupled cavity LINAC. And then the 80% of the acceleration is done in a superconducting LINAC using niobium cavities cooled to 2 Kelvin. So there's about 800 feet of that. And the LINAC is being done by Los Alamos and Jefferson Lab. Jefferson Lab does the cold pieces. They have a similar superconducting electron accelerator, and Los Alamos does the warm pieces and all the RF systems. Having accelerated H- ions up to 1 billion volts, we strip the electrons off and collect them in an accumulator ring, which doesn't accelerate. What it's doing is compressing the pulses. We get a millisecond pulse out of our LINAC, and then we wrap it 1,000 times around the compressor ring and spit it out in a single turn. So the pulse width goes down by a factor of 1,000, the pulse intensity goes up by a factor of 1,000. So we wind up with a microsecond pulse of protons, which we deliver 60 times a second to a liquid mercury target. The target is being developed by a group here in Oak Ridge, and the ring is being done by Brookhaven. The instruments that view the moderators surrounding the target are being done at Argonne National Lab. In addition to the neutron production and measurement infrastructure, we'll have a central lab and office complex that has shops and offices and so forth to support both the staff and the users of the facility. We'll support about 2,000 users a year coming to do experiments. Typically, about 70% of those are academic researchers. So a typical research group would be a faculty member and a couple of students and a postdoc maybe. The other 30% are from government labs and industrial research organizations. In addition to SNS, we're going to have a Center for Nanophase Materials Science, which is going to start construction in 2003. That's actually physically attached to the CLO, and that'll have things like clean rooms, electron microscopy, scanning tunneling microscopy, synthesis capabilities. So it's sort of the synthesis and characterization of materials that fits in very well with what we'll be doing with neutrons. The initial baseline for SNS is 1.4 megawatts, which is about an order of magnitude more powerful than the ISIS facility in the UK. In addition, we've left in the capability to add more accelerating cavities. The ring is sized to go to higher energy so that we can continue to increase the power over the operating life, and we'll be finished in June of 2006. When we're done, our goal is to provide a high availability, high reliability source of neutrons. It'll operate as a user facility, peer review proposal system. Anyone can propose an experiment, and when they come to do it, they'll have access to first-rate instruments and scientific staff. And we'll also be doing R&D to advance the state-of-the-art in both accelerators and targets, as well as instruments, which will keep us at the forefront. I think I'm going to skip over some of this stuff because I'm going to run out of time if I don't. This shows you an aerial of the site as it was several months ago, where we were starting to have some accelerator tunnels. These are now finished. The ring is finished. The target building is well along. We've started work on the CLO. We're now up to about 1.3 million construction work hours on the site without any injuries that would lead to a lost workday. In fact, just over the last year, things have really ramped up. This just shows the construction workforce by month, which is a good proxy for overall activity. And we're now up to anywhere between 500 and 600 construction workers on the site on a given day. This shows our safety celebration when we hit 1 million hours. We had 1,000 people in the tent who'd all been working on the site at one time or another. This shows some more recent views. This is a view down the LINAC tunnel, which you can no longer see because it's under 17 feet of earth. This is the Klystron gallery housing all the RF systems, central helium liquefier and RF facility, utilities building. This is where you go around the corner into the ring, which you can't see. It's also underground. The tunnel's finished. And this shows a view of the target building foundation with the liner of the target in place, and those windows that you can see, which I think I have in the next one as well. Oh, next one. We'll get back to that in a second. This shows the front end as it was shipped from Berkeley in July of this year. This is the medium energy beam transport radio frequency quadrupole. This is the building that it went into. This is now fully installed. It's pumped down under vacuum. It's undergoing electrical checks. We're going to begin commissioning it this fall. This shows some of the other technical components. These are the Klystrons that provide the RF power that goes into the accelerating structures, and this shows this target liner being installed. These windows here are the neutron beam windows out of which we extract our neutron beams, and they're just dropping this last piece of a sort of 7-section cylinder in place. This all gets filled up with steel, of course, for shielding, and then in the very center of it is where the target goes. This shows one of the cryomodules where we do the acceleration, most of the acceleration. JLab has actually demonstrated the performance of these things, and in fact they're getting accelerating gradients that are anywhere from 50% to 100% over our baseline requirements, so that's gone very well. One of the issues we've been grappling with is the lifetime of the stainless steel vessel that houses the mercury that is the target. And the issue there is something called cavitation-induced pitting. This shows an electron micrograph of a coupon of stainless 316 stainless steel. Before and after a beam irradiation experiment at the WNR facility at Los Alamos, and you see before it's quite pristine, and afterwards you have these little dimples. These are actually pits that have been excavated by mercury collapsing back into a void that's opened up due to the pressure waves traveling around in the vessel and the stainless steel. And so the issue has been, does this happen often enough and severely enough that it erodes the vessel? So we've had an extensive program looking at beam tests and also mechanical tests up to high duty factors to understand that. And the results are looking quite promising. This shows just an example, a measurement of the fraction of the area pitted as a function of the power level or effective power level. The crucial thing is the pressure pulse. What's the magnitude of the pressure pulse? And for 400 kilowatts, 1.2 megawatts, and 2.4 megawatts. And what you can see is there's not much difference in the amount of pitting between 400 kilowatts and 1.2 megawatts, but it goes up by almost an order of magnitude when you go up to 2.4, and it's even worse at higher pressure levels. This is good news because we're down in this range, especially when we first switch on. The other thing is that if you take a sample and do something called colsterizing, which is a chemical treatment that hardens the surface, then even at very high effective power levels, the fraction of the surface that's damaged drops way, way off. So it looks like we're going to get acceptable target lifetimes. In fact, we may well wind up being limited by radiation damage rather than pitting, but in any case, the pitting is not going to drive us to have to replace this thing so frequently that we get sick of it. One of the things we've been focusing on a lot is interaction with the academic research community. We have a lot of workshops. Most recently, we've been focusing with GINS, which is a joint UT-ORNL Institute for Neutron Sciences, in focused workshops in different areas of science where we bring in particularly people who don't have expertise or experience using neutrons, try and get them interested in doing experiments at existing sources and get involved in instruments at SNS. So we've had workshops on material science and engineering, biological systems. There's one on solid state chemistry and earth sciences planned for next spring. Another one on neutrons and nanoscience, and then in the longer term on the interest in the neutron itself rather than things you scatter from. We had a conference here in Knoxville in June. We had over 400 people for the first American conference on neutron scattering, so we're trying hard to get people engaged. We're building some scattering instruments as part of the construction project. We're also working with the research community to develop additional instruments. There's currently 3 that are funded. One is led by Caltech, another one by Penn State, and a third by McMaster University to build 2 inelastic instruments and an engineering materials diffractometer, which I'll probably say a little bit about. And there's more of these that are in the pipeline in various stages. So this shows the instrument scheme as it stands at the moment, and I'll say a little bit about, maybe 5 minutes before I finish up, what the different types of instruments are. We're building, as part of the construction project, the instruments shown in yellow, and there are a total of 5 of them. There's a backscattering spectrometer, which is an inelastic instrument with quite high energy resolution, about 2 microelectron volts. So its dynamic range kind of begins where NMR runs out of steam. 2 reflectometers for studying surfaces and interfaces and multilayers. So that might be magnetic multilayers. It could be membranes. Small angle scattering instrument for studying things that are big, like proteins and polymers. And a powder diffractometer for doing structural refinement of crystal structures in polycrystalline samples. The red instruments, and there's supposed to be 3, the engineering diffractometer and the 2 inelastic instruments, are the instruments that are the currently funded instrument development teams. And there's another 5 shown in white that look like they're going to get funding in the fiscal year that starts in October, looking at things like a high pressure diffractometer, this is of interest to the earth sciences community that wants to be able to study crystal mineral structures primarily, pressures and temperatures that are sort of getting into the closer to the core of the earth. There's disordered materials diffractometer for studying liquids and amorphous materials. And single crystal diffractometer for studying proteins in inorganic crystal. Must be running out of time here.
What it is they have class.
Yeah. So I said a little bit about these. Maybe I'll just summarize by showing you some of the sorts of range of science that you cover. In the inelastic instruments, you're looking at length scales between 1/10 of an angstrom and a couple of hundred angstroms. And time scales that range from about 10 to the minus 8 seconds to 10 to the 16. That's the footprint, sort of in the middle of that is the footprint of the inelastic instruments that we're building. And that includes things like lattice vibrations. It includes things like diffusion, molecular reorientationing, tunneling spectroscopy. So this is sort of the realm of chemists. You may be more of a physicist if you're up here looking at itinerant magnets or lattice vibrations. And getting down here, you're looking at large-scale motions of polymers and biological systems. If you do the same thing, I'm just skipping ahead here, for the elastic instruments, then here this is plotted in terms of length scale, and it's a pretty wide range, about 0.1 angstroms up to about 10,000 angstroms. So it's sort of the whole range of what we now call nanoscale phenomena, and Q resolutions that tend to be, fractions of a percent. So quite good Q resolution, and this shows some of the scattering instruments, powder diffraction, reflectometry, and sands. You have crystal structures, magnetic structures, liquids and glasses, membranes, magnetic thin films, and multi-layers, micelles, colloids, vesicles. Maybe say a little bit about the engineering diffractometer, since that tends to be something that nuclear engineers have used in the past, at least in some cases. The instrument there, which is the one funded by the Canadian funding agency, CFI, is called Vulcan. It's shown in cartoon form here. It's a powder diffraction instrument, but what you're doing is using powder diffraction to measure not crystal structures, but simple lattice spacings. And of course, what happens is if locally in some region of material there's a compressive strain, then the lattice spacing is reduced, and if there's a tensile strain, the lattice spacing is increased. So you can actually measure that just by looking at the Bragg peak, which the scattering angle or the wavelength at which you Bragg diffract tells you what the lattice spacing is. You can probe that in a pretty small volume of order a cubic millimeter and raster scan that gauge volume through some intact component, so you can make a three-dimensional map of the residual strains, and you can actually do it in all directions, so you can get the strain tensor, and then if you know Hooke's law, you can determine the stress. The residual stresses are important because they can lead to failure. So people do measurements where they may take a 7.7 landing gear that's been forged and quenched and machined and had all kinds of stuff done to it, and it can have residual stresses. You can map those out in three-dimensional space, or you can study the stress field around a rivet or a crack or something like that. And you do that with an instrument like Vulcan that has a lot of detectors sitting at 90 degrees because you want to have a well-defined gauge volume, which is the intersection of your incident beam and your scattered beam. Then it's got this 3D computer-controlled table to raster scan your large thing through this little pencil beam, or maybe it's even smaller than a pencil beam. This one also has the possibility of adding a small angle scattering detector so that at the same time you're probing lattice spacings, which is a sort of small length scale thing, you can study microstructure to look at grain boundary effects and so forth in the sands, and you can do that in situ, so you can put on load frames and furnaces and that sort of stuff. It's a very fast diffractometer, so you can do kinetic behavior. In principle, we could do single pulse diffraction, which means you get a pattern every 16.7 milliseconds. So this will be a very capable instrument that'll be of interest to a broad range of the engineering community. And certainly, actually, a lot of this technique was developed by people interested in reactor materials, looking at things like pressure tubes and stress corrosion cracking and all these kinds of things. So I expect that will continue to be the case. So I think I better stop there. I won't say anything about the Nano Center and say that where we stand at the moment, we're halfway through in terms of actual completed work. In fact, today we're at about 50%. It was 49% last month, so should be 50% by today. We're actually about 86% through in terms of awarded contracts, so we're getting over the hump. We're holding together in terms of contingency and schedule. We got about 20% contingency on the work to go. We're working to finish in December of 2005 to make sure we finished in June of 2006, and the capabilities of the machine are going to be outstanding and meet all the needs of the scientific community when we get started in a few years' time. So, happy to answer any questions.
Okay, we have time for a few questions.
What is the physical size of the target?
The cross section it presents to the beam is 8 by 20 square centimeters, and the active volume is, I don't know, half a meter or something. There's a much larger mercury process system. We're continuously circulating, so it extends on back into a hot cell, but that's not the active part of the target. And the vessel is 316 stainless steel, so it's sort of a well-known material that's pretty well characterized. The new wrinkle is this cavitation that occurs in the mercury. But in terms of radiation damage and stuff, it's pretty well understood.
Okay, I have a question. What about cost to a user? You have this professor and postdoc and 2 graduate students. Do they have to pay to get access?
As long as the research is going to be published in the open literature, there's no charge for the use of the beams. Now, they may have costs associated with making a sample or traveling to the facility and that sort of thing, but there's no charge for the beam time. If it's proprietary, then it's a different story. You've got to do sort of nominally full cost recovery, although it's really just full cost recovery in terms of the operations. You don't try and amortize the facility. So it's still a fairly good deal, but it's not cheap.
Yeah.
It'd be, $5,000-$6,000 a day or something.
Okay, one more question. Alan?
Have people already started applying for beam time?
No, we don't have. We're still 4 years away, and so the problems that are interesting now will be different in 4 years' time. The thing that is happening is, of course, we're selecting the instruments. And actually, when we're done in June of 2006, we will have made our first neutron. So we won't, at that instant, be immediately a fully operational user facility. It'll probably take a year or two after that to really crank up the gear on the user program. And, we've got to get the accelerator reliability to the point where people can buy a non-refundable airplane ticket to come and do their experiment.
Okay, I see at least one new face in the audience, and you may not know that we do have refreshments downstairs, and everyone's invited. But before we adjourn for refreshments, let's express our appreciation. Hang around.
Yeah.
Refreshments, good. Let's. I'll show you.
We're scores.
That's one.